Hello, this is Dr. Christy Patton-Lokes. Welcome back to Material and Energy Balances. In this lesson, we're going to finally get started on the energy balance portion of this course. Next, let's talk about how we can do an energy balance using these various terms. Now, energy is a conserved property just like mass, and so I can do a balance on my system. Now I'm going to have some energy that's contained in the system, and it might change over time. So total energy could change over time, and this would be like an accumulation term. And energy can come in and it can go out. But energy can't really change into something else. It can. E equals mc squared is certainly valid. However, that is A, not typical for most chemical engineering problems, but B, it's on a scale that does not suit most industrial scale. So I can neglect the changing into something else piece, and so I have N, stuff that comes in either goes out or it accumulates inside my system. Now, the types of energy, if I limit myself to a system with no flow, so there's no flow, and if I have no flow, I am going to call that a closed system. No flow. Well, we meant to write flow. We'll try again. So this is a closed system if there's no flow. And so, therefore, the accumulation is going to be a change over time of the total energy. This is my change over time of my total energy. And if there's no flow, the only way energy can be exchanged with the surroundings is through that heat transfer and the workflow. And so therefore, this is going to be the exchanging with the surroundings. And in this case, the delta, because I'm looking at a change over time, is going from the beginning time to the ending time. And so when I do the subtraction, if I said, say, delta U, it doesn't matter which of these, this would be U at the end minus U at the beginning. Okay, so delta is always meaning end minus beginning, because that's the way this is defined. Now, if I have a system where I have flow, then I'm going to call that an open system. So now I'm going to have flow. There are many, many cases, and we're going to only for this course do the case where there's no accumulation. So this is going to be also called a steady state problem. And in the steady state problem, I have flow, but I have no accumulation. So in that case, I have in and out, but the energy inside the system stays the same. Okay, so then what happens on my energy balance? Well, some of the energy is going to be carried in by the flowing stream. Some of it's going to be carried out by this flowing stream. And it carries energy, which is going to be the total energy, which is U plus KE, or no, E sub K plus E sub P, and that's going to be the total energy that's being carried. But there's also some energy that's required that's pushing the molecules along, and that energy is going to be PV. And development of that is going to be left for other courses, say a thermodynamics course, but there's also this PV term that's going to be a portion of the energy, and it's the energy that's pushing the molecules in and out of the system. And there's always this plus PV on the inlet and on the outlet side. It's work. It's a form of work. But U plus PV show up so often that they are defined separately as H equals U plus PV, where H is defined as enthalpy. Whenever you see an equal sign with an extra bar, that means it's it's true by definition. So H is defined as enthalpy, and it's U plus PV. And so the energy that flows in and out is H and EK and EP. We define, therefore, that energy flowing in and out as delta H plus delta EK plus delta EP. But now that I'm not talking about a beginning and end of time, remember I said there's no accumulation. This is steady state. In this case, that delta represents the change from the inlet to the outlet. On the other hand, I still have potential for energy to flow in and out to the surroundings through heat transfer and work. Now let's talk about kinetic and potential energy calculations. You've done these before in other courses. We're going to take a mass and we're going to define it as being m. If it moves at velocity v in a gravitational field with gravitational acceleration of, say, 9.8 meters per second squared, 32.2 feet per second squared, at a distance z above a reference plane, wherever I've defined as my reference, then the kinetic energy is 1/2 mv squared, and we can convert by G to more natural units by dividing by G sub c. And potential energy is mgz, and again, converting that by dividing by G sub c. Now, G sub c is just a conversion factor. We've used it in the past. It's just a reminder to adjust the units to energy units, because otherwise the units are sort of weird. You get, right, well, let's look at this. So kilograms, if I work in SI, times G, so that's meters per second squared, times meters. And a kilogram meter squared per second squared is supposed to be energy. Okay, and so G sub c helps us remember that we have to adjust our units. Now there's going to be a lot of vocabulary that comes up. And at this point, we're just going to sort of define things fairly quickly. You're going to get really used to this. By the time you graduate, these terms will be so natural to you. But for now, these may be the first time you've seen them. So one of the special cases we frequently use is that a system may be well insulated. If it's very well insulated, there will be no heat transfer in or out. Now, the reality is there will be some heat transfer, right? You can have a really awesome ice chest, but your stuff won't stay cold in there indefinitely. There will be some heat transfer, but it can be very low rate of heat transfer. And in those cases, when we say well insulated, we're frequently going to use well insulated to mean that we can call it Q equal to 0. There is no heat transfer, and the word we use for that is adiabatic. Another special case is when a system has no movement, okay? In that case, we say that the work is 0. Work somehow needs to be able to be thought of as something, like I say, that could lift a weight. And so I need to be able to move things. So if there's nothing moving, there will be no work. And then we're going to have these energy terms. Delta, well, the kinetic and potential energy are easy to define. We have equations for those. But internal energy and enthalpy are kind of weird and hard to understand at this point. So these are going to be functions of the pressure, temperature, and composition of the material. For solids, liquids, and ideal gases, the pressure isn't going to make a lot of difference. So we can frequently not worry about that. And if we stay with pure substances, then composition won't even change. If pressure is not going to be an issue, so solids, liquids, and ideal gases, if there is no delta T, if it's isothermal, okay, so same temperature, Then delta H, delta U will both be 0 for the cases of solids, liquids, and ideal gases. And finally, what I want to talk about is tables of thermodynamic data. A lot of the material that you're going to study is going to be on substances that are very well studied. And so we can look up values that people have measured historically for HU, specific volume, for a wide variety of temperatures and pressures. And if an entry doesn't show up on the table, you can use linear interpolation to estimate it. And we covered that back in Unit A. Now, this data all is going to have a reference state, which is simply some place where someone says, oh, at this point, I'm going to decree U is equal to 0. There's not a particular place where U should be 0, so it's just easier for calculations if you just simply choose a basis. Now, in this particular textbook, the reference state is the triple point of water, which is when the temperature is 0.01 degrees C and the pressure is 0.0061 bar. But in another textbook, the reference state is going to be different. Main caution about that is, all data you use needs to come from the same table. And at least it should have the same reference state. So one table will have a common reference state. If you need to go to another table and it has a different reference state, they're not going to be usable for the same problem. Now in your book, there's only a little bit of data available like this. They have steam tables for water, liquid and vapor water, and superheated steam. Let's just briefly look at these. So saturated steam tables, they have saturated steam sorted by temperature is the first table, and a couple of pages later in the book, if you have a hard copy, or scroll on through the appendix to get to another one that's sorted by pressure. So I've shown you the one that's sorted by temperature, and they have specific volume, specific internal energy, and specific enthalpy. And they show you what those numbers are for the liquid state and for the saturated vapor state. They call it water and steam, but liquid and vapor. And for enthalpy, they also show an evaporation, which is simply the difference between these two. So they've subtracted to get this. And we'll talk more about this column in a few lessons. Once you get past saturated liquid vapor water, remember we hit that critical point. So you might want to go back and review from chapter 5 where these transitions occur. But once you get to the critical point, or once you heat the substance beyond that saturated vapor state, you now move into the superheated steam. And so this could have a wide variety of temperatures and pressures. The others, temperature and pressure, were all correlated. But here, for a particular pressure, so let's take 0.1 bar, they show me what the saturation temperature is. So 45.8 is Tsat. But for this pressure with this temperature, this is HU and V. For this pressure at this temperature, this is HU and V, and so forth all the way along. Now the way this is set up in this textbook, everything above this line is superheated vapor, and everything on the other side is going to be compressed liquid. Okay. Some books don't include all of this data. Every book is going to be set up a little bit differently. So try looking at these and puzzling it out and making sure they make sense to you. We'll be starting to use these in the next lessons.